I'm concerned only about the rate. Rate is the only thing that is in my mind now, right? So if I at the macroscopic level, I'm not going in the molecular level, at a very bird eye view level, you can see it. Bird eye view. Only from a distance I am seeing it. There is a container and something is happening. Like I'm just seeing the quantity of reactants, quantity of product. Those things I'm seeing, then I call it a macroscopic level. I'm not even concerned about which molecules are reacting, why they are reacting. I'm concerned only at the macroscopic level, right? I'm only interested in the amounts of the reactant reacted and the amount of product formed, right? Amount of this, amount of this. That's what I'm interested, and that is what we call macroscopic level. But when you talk about the microscopic or molecular level, where you actually want to see the molecules, how it is taking part, how they're reacting, right? So if you see for a given reaction, if you go inside any reactant will have atoms and molecules, correct? So you want to see what is happening, what is actually happening inside, why A plus B is becoming C and D. So if you see the molecules of A are in blue, B in red, C in green, and D in red, you see they are reacting, right? They are bumping each other, and they are forming new products. This is something at very microscopic level or molecular level we call, because here in this level we are concerned about the reaction mechanism, how it is reacting, right? Their orientation, the energy of these molecules, and how they are getting undergoing collisions, and what is the effective collision, which is non-effective collision, how the product is getting formed, all those kind of things. Role of catalyst also, how the catalyst is helping to increase the reaction rate. So this is all molecular level. So in chemical kinetics, we'll discuss the reactions both at macroscopic level and molecular level. Correct? So in this whole chapter, we'll first start with macroscopic level. We'll talk about the change in the product or change in the reactant concentration. And once we understand the concepts, why the products are, how the rate of change of product is linked with other parameters, then we'll start at molecular level about how the molecules interact and the product is getting formed. Correct? So molecules at the molecular level, I will assume the molecules as car, and the bumping of molecules which you see here is similar to bumping of cars. Correct? So if you see, these are my cars, and if the car bump each other at a very high speed and they almost ramp each other, right? They break one another, then I'll call a reaction happen, right? For example, in this case, you see the two cars. In the first case, if you see, these two cars ramped and the reaction happened. But in the second case, if you see, the cars didn't even touch each other. So there was no reaction here. So there was no reaction here, and there was a reaction here. So in the whole chapter, we'll consider molecules as car, and we'll try to understand how the reaction is happening, right? We talk about the feasibility of the reaction. In this case here, the reaction was feasible. Here it didn't happen. If we talk about the extent of the reaction, then we'll talk about the number of cars we have, right? The blue cars and the red cars. And that will define the extent of the reaction. If we talk about the speed of the reaction, then also we'll talk about a lot of factors. Just be with me. We'll try to visualize molecules as car in the whole chapter, and the way the molecules bump each other, there's nothing like the bumping of two different cars. And the final broken car is my product. We'll assume in that way we'll see the whole chapter, right? The bumping of car, this becomes a new product. So since I told that we'll talk about molecules as car in the whole chapter, let's see. In a car, what is there? Car runs, right? There's a speed of the car. For example, this is a car, and this is my distance time graph I have made, and there's a car which will move from here to here. And if you see, as the time goes, car will move from point A to point B. So this is my point A, and this is my point B actually. So if you see, the car is moving from point A to point B, and it's going up, and now it's stopped. But the time is getting continued stop, and then again it's going up with a higher speed, and it pauses for some time, and then again it goes up, and it stops. This is the distance time graph. You see, this is the distance covered. Let me repeat once again. The car starts, the car accelerates, and then it stops. It stops for a certain time, the time goes on, and then the car again starts, again goes off, stops for some time, again the car starts, and then it stops. So if you plot the distance time graph, this is how it will look, right? Now if you see in this whole journey, if you talk about the average speed of the car, that is nothing but total distance covered by car, that is AB, by total time. This is my point here B. If you plot the xy point here, this x will be t and y will be point B, correct? And here it will be t will be 0 and point A. So if you see, the total distance covered is AB and total time is t. So if you talk about the average speed will be total distance covered by total time, and that is nothing but AB by t. Hope it took 2 t seconds to come from there to there. That will be the average speed, correct, from point A to B. But now if you want to find the instantaneous speed, and you must have studied this in the physics chapter, the instantaneous speed at any point is nothing but from that point you draw a tangent, and the slope of this tangent will give you instantaneous speed, that is dx by dt, right? That is speed instantaneous. Correct? This is a very simple concept we have learned in physics, average speed and instantaneous speed. If you have not studied and if you're not understanding from the slide, you can watch the physics video where we explain the instantaneous speed and average speed. So here we have this instantaneous speed for at any given point. For example, here also you can find the instantaneous speed. I just have to draw a tangent here, and the slope of this will give you an instantaneous speed. At this point, if you see, the tangent will be in this direction and the speed will be 0. At this point, the instantaneous speed will be different, right? So if you see, here it is accelerating, it has more speed, here it has almost 0 speed. So at any given point in time, you can just draw a tangent and you'll get the instantaneous speed at this point of time. Similarly, in the reaction also, we will find the average rate of the reaction and instantaneous rate of the reaction. As I told, the molecules are nothing but car. You're just comparing. The car has average speed, instantaneous speed. So the reaction will also have average rate and instantaneous rate. So if you see, this is a typical reaction we have. So if you see a typical reaction, I have a reactant on my left hand side, product on my right hand side. Over a period of time, the reactant will diminish and will get more product. So if you see this graph, the concentration of reactant goes down as the time increase, and the concentration of product in the red one increase as the time increase. The green one is my reactant and the red one is my product. That's my typical concentration time graph for a given reaction. So if you see, for any kind of reaction, if you define the rate of a reaction, the rate of a reaction will be nothing but change in amount of chemical species. It can be species, can be anything, reactant or product, right, during a reaction. The whole thing divided by time in which change was caused. For example, you mix hydrogen and oxygen and get water. The reaction took only 2 seconds, but you're observing it for maybe 30 minutes. But the reaction time will be 2 minutes because of the 2 seconds. Because at 2 seconds only, actually the reaction happened, right? For example, you have hydrogen and oxygen, it gives water. And this took only 2 seconds. Correct? And after that, it was just water and you were just observing it. So it is not the time you are observing, it is the time when the reaction is happening actually. So that is the time you will divide, and this is the change in amount of chemical species during a reaction. For example, you talk about the decrease in the concentration of hydrogen, or decrease in the concentration of oxygen, or increase in the concentration of water. So as we have told, a chemical rate of reaction will have average rate of reaction, and we have again instantaneous rate of reaction, similar to car, average speed, instantaneous speed. So let's talk about the average rate of reaction, right? So average rate of reaction is nothing but the rate of decrease in concentration of any of the reactant, because the concentration of reactant will decrease, or the rate of increase of concentration of product. Correct? Either rate of decrease in concentration of any one reactant, let's suppose you have A plus B is equal to C plus D, or let's suppose you have A plus B here and you have C plus D here. So when we talk about the average rate, there is nothing but the rate of decrease in concentration of any one of the reactant, for example A or B. Correct? So if you say, if I want to write average rate is nothing but minus delta N, because the number of moles I am talking about of reactant, by delta T, or you can say delta N of product by delta T. Please note there is a negative sign here and there is no sign here. There is a positive sign here. Why there is a negative sign? Because if you see, the reactant will decrease. For example, at T is equal to 0, it was, let's suppose, 10 mole and it was 2 mole. At T is equal to T, this will become, let's suppose, 5 mole, and let's suppose this is increase, it becomes 6 mole. So if you see, the change in the reactant is what? 5 minus 10, there is minus 5. So since there is a minus here, to remove that minus we are putting a negative sign. But if you talk about the change in product, final minus initial, 6 minus 2, that is 4. Already a positive quantity. Let me repeat once again. The change in reactant, final minus initial, that is 5 minus 10, that is minus 5. So to get rid of minus sign, we'll put a minus sign here. Change in products, final minus initial, that is 6 minus 2, that is 4. That's a positive number, so we don't put a negative sign here. Correct? So both are nothing but average rate. You can just either take the rate of decrease of the reactant or rate of increase of the product. Both are nothing but the rate of reaction. Let's talk about the instantaneous rate of the reaction. See, again, instantaneous rate of the reaction, as I told, it is nothing but at any given point of time. For example, if I want to know here I can find minus dr by dt. So dr by dt will be this much, you put a minus, you will get this much, this low. This is my instantaneous rate of reaction. Or if you find for the product, it will be plus dp by dt. Why plus and minus? The same rule which we have just explained. Since this is, this is my dr by dt, this line, but the moment you put minus, the sign changes. Right? It becomes something in this direction. So you see, both are in the same direction at any given point of time. So rate instantaneous is nothing but either minus dr by dt or plus dp by dt. Both are my instantaneous rate of the reaction. Right. One thing to note here is, when I talk about the average rate of reaction, it doesn't mean that you have to talk about the average rate from here to here. I can also talk about the average rate from here to here. This point is, for example, this point is A, this point of B. I can also talk about the average rate between A and B. So in that case, I'll find the concentration at B and find the concentration of A. For example, in this case, average rate from A to B will be what? Concentration, that this be R at B minus concentration at A by delta T. How much time it took from here to here? That is, it took this much time. Correct? And since if you see RB will be less than RA, there has to be a negative sign because it's nothing but for the reactants. For reactant it was minus of delta reactant by delta T. So this is my average rate between these 2 points A and B. Correct. So when you talk about the average, you have to talk about the average rate of reaction between 2 points. When you talk about instantaneous, you have to talk about instantaneous rate of reaction at a given point of time. Right? 2 point average, 1 point instantaneous. Thank you.